Hello everyone. In this video, we will talk about exploratory data analysis. Exploratory data analysis, or EDA for short, is the process by which we explore and investigate datasets. I'm going to refer to it as EDA from now on during this video. We can summarize datasets' main features, often through data visualization techniques. We can understand how to manipulate data sources to answer specific questions by identifying various patterns, detecting anomalies, test different hypotheses, and validate assumptions. EDA provides a clearer understanding of variables and their relationships. It also helps us decide what statistical methods to choose for analysis. I liked a lot this quote from Sherlock Holmes, Sir Arthur Conan Doyle, which says, "You know my methods, Watson. There was not one of them which I did not apply to the inquiry, and it ended by my discovering traces, but very different ones from those which I had expected." So I would like you to have this attitude when you start exploratory data analysis with a new dataset. The role of EDA is really to examine data without making assumptions up front. It helps uncover obvious errors, spot patterns, identify outliers or anomalies, and explore relationships between variables. EDA's primary purpose is to explore data before any assumptions are made. By performing EDA, we can make sure the analysis results are valid and aligned with our goals. It also helps us confirm whether we are asking the right questions or not. EDA can answer questions about standard deviations, categorical variables, and confidence intervals. Once insights are gained from EDA, they can be used for more advanced analysis or modeling, different ML or AI techniques. But now, let's look at different principles of EDA. There are 4 principles of EDA. Though we will explore various methods useful for analyzing data later in the course, they all share some common characteristics, which are central to the philosophy of EDA. These principles, they are also known as the 4 R's because they each begin with the letter R. So let's look at the first one. Revelation. In EDA, there is a strong focus on using graphs to uncover patterns or representing fitting. Visual data displays and can communicate insights that numbers alone cannot. A key rule is to always graph your data before calculating any summary statistics. We will engage in extensive graphing and discuss effective graph design later in the course. The second R is resistance. So EDA aims to describe the overall pattern within the bulk of data. In this process, we don't want unusual observation to disproportionately affect our results. So, our methods must be, so to say, resistant or unaffected by outliers. For instance, when examining a set of numbers, the median is a resistant measure, while the mean is non-resistant, since it can be distorted by extreme values. The mean, can be distorted by extreme values. Now the third R is re-expression. So the original scale on which data is presented is not always ideal for plotting or summarizing it. Often, data needs to be transformed to a new scale using methods like taking the square root or applying a logarithm. There are different classes of re-expressions which can be used based on the data you have at hand. And then the fourth R is residual. During data analysis, we often find an overall pattern which we call the fit. While this pattern can be very informative in EDA, we also focus on deviations from this general pattern. These are called residuals, calculated as the difference between the observed data and the fit that I mentioned earlier. And to be honest, investigating residuals can often be more revealing than the fit itself. And now let's look at different type of analysis. So we have univariate analysis, bivariate analysis, or multivariate analysis. And we're going to look at each of them. So univariate analysis is regarded as one of the most basic analytical methods that we can take into use. It usually serves as the initial step in exploring any dataset. And the goal of univariate analysis is to examine each of the variables independently before we progress the analysis of multiple variables together. This type of analysis, as also more complicated analysis, can be done even in Excel. And I must say here that if you master Excel, you can do some really amazing analysis just there, but that's for another time to discuss. It's not really good Excel, I mean, with extremely large amounts of data, but with limited univariate data, it can work very nicely. Also, we have other statistical languages like SPSS, SAS, and R that are often used by biologists and social scientists, and also statisticians to employ various univariate techniques. The goal of univariate analysis, to get back to it, is to describe data. And I would say there are four big groups of techniques that we can use here in univariate analysis. So first of all, we have summary stats. And here we can have different measures. For instance, a measure of central tendency. Here we have statistics like the mean, the median, the mode that we discussed about in a video last week, which summarize the data with a single representative value at the center. Then we can have measures of variability. So we can assess how data varies around the central value. And we do this by calculating specific univariate statistics like the range, the interquartile range, variance, standard deviations, and so on. And the third one could be the measure of shape. So the shape of the data distribution provides us with valuable insights, and it also helps us identify the type of distribution the data follow, which can be very important. By examining the shape, we can determine if the data is symmetrical, if it's asymmetrical, if it's skewed or not, if it's skewed to the left, if it's skewed to the right. We're going to see more details about that later, and whether it has positive or negative kurtosis, among other features, and so on. And these summary statistics can be applied to calculate metrics such as the proportion of missing values, the upper and lower bounds for detecting outliers, the degree of variability using the coefficient of variance, among other things. Another class is tables. These are very useful in univariate analysis, particularly for categorical data or numerical data with low cardinality. And there are different types of tables that we can include here. So we can have frequency tables, which are tables that display each unique value and its corresponding frequency in the data. And these are providing a summary similar to a histogram, a frequency bar, or a pie chart, but this is in a tabular format. Then we can have grouped tables. So instead of counting each unique value, values are grouped or binned. We will hear this term of bin throughout the lecture. And this table reflects the frequency of each group. This method also is commonly used for numerical data with high cardinality. Percentages or proportion tables. So instead of showing the frequency of unique groups or unique values, we can display tables with proportion of each value or each group in the data as a percentage. And then we could have cumulative proportion tables. And this is typically used for bin data with a specific order or for ordinal categorical data or so on. And now let's look at graphs. So this is the third category. Different types of graphs can be used to analyze and interpret data. So there are some common graph types here that we are going to look at more in detail later on in this lecture. And for instance, there are histograms that show the frequency of individual values or groups of values. helping to visualize, for instance, the distribution of data. There are box plots, which provide key information like the minimum, the maximum, the median, the first quartile, third quartile. These are also very useful at identifying outliers. Then there are density curves, which illustrate the shape of data distribution. So we can see that if the data is distributed normally or if it's skewed. We have bar charts that are used primarily for categorical data. We have pie charts that are similar to bar charts, but display frequency of categories, both in a circular format and then with each slice representing a category in the data and so on. And then the fourth and more special case would be inferential stats. And very often, if you think about it, the data we're dealing with is just a sample or a subset of an entire population. And then this poses different questions, like, can the results from the sample be generalized to the population? In other words, is the sample representative of the population? Or has the population changed maybe in the meantime? These kind of questions are addressed through hypothesis testing. And these hypothesis tests are specifically designed to handle univariate data. Also, there are designed for other type of data, but we are now talking about univariate analysis. And here we can look at a few tests that we can use in very specific situations, like the z-test, which is used for numerical quantitative data with a sample greater than 30 usually, and population standard deviation that we know. We have chi-square test, which is used with ordinal categorical data. We have the Kolmogorov-Smirnov test, which is used with nominal categorical data and so on. But now also let's look at bivariate data. So bivariate analysis is used when we examine the relationship between two variables. This type of analysis focuses on understanding how these variables affect one another, how they are related, how they compare to each other, and so on. Similar to univariate analysis, which also uses graphs and tables and statistical methods, statistical measures, bivariate analysis also employs various tools like scatter plots, bar charts, multi-line charts, pie charts, and then also tests like t-test, independent t-test, one-way ANOVA, and so on. When we look at the two variables, we have to make sure, if you look at this figure right here, we have to make sure that we are not mixing up correlation and causation. And you probably have heard this before. Correlation does not imply causation. This is something that we have all heard. But think about this. Is ice cream consumption linked to shark attacks? So let's take this example. If you think about it, as the outside temperature increases, we consume more ice cream. People also spend more time near water bodies during warm months or oceans where we can find sharks. And this might lead to more shark attacks. However, just the fact that the shark attacks increases in the same manner as the ice cream consumption increases, this does not mean that either of them is causing the other. This could mean that they are only correlated. And now let's look at correlation, which is very specific to bivariate analysis. We can have positive correlation, which means that there is a linear relationship between the variables and it's positive, and the two variables increase or decrease in the same direction. This is the positive correlation. Then we have negative correlation. That's just the opposite of it. So we have a relationship, we have a linear relationship, but the slope of the line is negative. So the variables change in opposite directions. One variable decreases and the other variable increases. And there is the third option, there is no correlation. The variables have no linear relationship. Now let's look at what kind of plots we can have here that are mostly used in this bivariate analysis. So a scatter plot, for instance, helps to visualize the relationship between two continuous variables. And if we look at what kind of scatter plots we have here, we have the relationship between the tips and the total bill that people pay. So this would be like, for instance, 2%, 4%, 6%, 8%, and so on of the bill. Another type that is quite used is in the context of time series especially are the line graphs. And this is compared to variables over time. This helps in identifying trends, identifying cycles, identifying patterns that appear in the interaction of these variables over a specific period of time. So if you look here on this graph, you can see the price varying from the 1910s until the probably 70s. Then another type of graph is sorry, not of graph, but here it's in a graphic format, but of representation of bivariate analysis is cross tabulation, and this is also referred to as contingency tables. Largely can also be represented as a heap map, like you see here, and is a method for examining the relationship between two categorical variables in our case. So it shows the frequency distribution of one variable's categories across rows and then the other ones across columns. As you can see here, the education level and the gender. And this facilitates the analysis of the relationship between these two variables. Now, if we look at multivariate analysis, there are different types of analysis that we can employ here, but these two are very common, and we're going to look at some of them more in details later. Principal component analysis. This is a supervised method that is used in machine learning for feature extraction and also in other types of EDA. And this aims to reduce dimensionality, and it does this by selecting a subset of the most informative features from a dataset with many variables. So here you can say in this dataset, we initially had 4 dimensions, and this has been reduced at 3 dimensions through PCA. Why this is important is because if you remember from the last lecture, higher dimensionality can lead to this curse of dimensionality. So we cannot really perceive as humans very well or at all almost. Maybe we can imagine 4th dimension time if you think about it, but further on we cannot really exactly perceive it. So it's good to do visualizations in like 2 dimensions, in 3 dimensions, so that we can easily interpret them and visualize them. Then another type of analysis that can do, or more or less graphs that we can employ, are display plots. And these display relationships among multiple variables at once, providing a thorough view of potential interactions. So you have all kinds of plots that you can employ in this kind of like matrix format. And you can interpret them either separately or together, and you have a more comprehensive view of your dataset. This can easily be done in Seaborn almost automatically, so I highly recommend that you use that when you have the chance to implement something. But we talked about skewness earlier on, and this is a very, very important concept. So I'm going to go through it a bit more in detail. So what is skewness? It's essentially a measure of asymmetry of a distribution. So categorizing or measuring accurately the skewness offers insights in the distributional values around the mean and affects the selection of statistical methods and data transformations that we have. For instance, distributions with high skewness may be improved through normalization or scaling to approximate a normal distribution, as you can see here. And this can enhance not most of the time, but a lot of the time can enhance model performance. So there are three types of skewness, and we will start with the down one in the middle, the normal one, or the zero skewness, the normal distribution, which is zero skewness. This is a symmetric distribution with values evenly centered around the mean, as you can see. There is no skew, it's lean, and there is no tail to either of the side. The median, the median, the mode, and the mean are all at the center point. Now, in practice, in the vast majority of the time of the cases, the mean, the median, and the mode might not align perfectly in a straight line, but they are very close to each other, so we will consider that as a normal distribution. They may be a little bit dispersed, but if we consider in that particular context that the differences are generally too minor to have a significant impact, then we can consider it without a skewness, we can consider it normal. And now let's look at the right side of the slide. So in a distribution like this with positive skewness, like the one on the right, this is also called right skewness, as you can see here. We have a long right tail. So the right tail of the distribution is longer than the left, clearly, as you can see here. This is it. And the meaner is also greater than the median is also always greater. The the other way around. The mean is also greater than the median, and the mode is also lower than the mean. And then the lower values are clustered in the heel of the distribution, while extreme values are in the long right tail. So extreme values, you will find them here. Now, if we look at the graph on the left side, so over here we have a distribution with negative skewness or left skew with a long left tail, as you can see. Here, the mean is less than the median, and then the mode is greater than the median. And of course, because the median is greater than the mean, and the mode is also greater than the mean, obviously. Higher values here are clustered in the heel of the distribution, while extreme values are in the long left tail, so over here. So to distinguish between positive and negative skewness, we can think about this. So to raise the mean of a distribution, we need to add values significantly higher than the mean. And the other way around, to lower the mean, we should include values significantly lower than the mean. If most of the extreme values are higher than the mean, then the skewness will be positive because these values push the mean up. If most of the extreme values are lower than the mean, the skewness will be negative because these values pull the mean down. Okay, but enough about this. Now let's move on to histograms. So a histogram is very suitable to visualize distributions of numerical data over a continuous interval or a certain time period. The data is usually divided into bins. Each of the bar in a histogram, so as you can see here, these bars, all of these are bars, represent the tabulated frequency at each bin. So we were talking about these tabulars earlier on, if you remember. These histograms can give you very useful information. You can see where the center is pretty much all the time. You can notice the variability, the skewness. You can also detect the outliers. And in Matplotlib, as you can see, you can have 4 options for displaying them. The step field, the step type, the bar stacked, and with the unequal bins. The histogram organizes large amounts of data and produces this quick visualization using a single dimension. So it is often the method that we immediately run into when we get a new data set, just to get the very first insights into our data. All right. So we can also plot histograms with multiple sample sets. And then we can use legends with multiple sample sets. Like this, we can use stacked bars. We can use different things. We can use step curve with no fill. We can have data, different sample sizes and so on. So we can select different bin counts. We can do a lot of things with this, and they're very evocative a lot of the time. But now, they're not the answer to everything, obviously. So for small data sets, they can be very misleading. They are effective when we have one variable at a time, but they're much better with large data sets. They're quite useful because you can see general properties of the distribution. Just by looking at the histogram, you can see if it's skewed or not, like I said earlier on. But if you have many variables at a time, I urge you to also employ other EDA techniques that we talked about and that we're going to talk about more in the future, because histograms, after all, are not always so informative. But you can get a lot of information also looking at just one variable through box plots that we're going to talk about next. So a box plot is very suitable to compare range and distribution for groups of numerical data. And it is essentially, as you see, a box with whiskers. These are whiskers with a center line in the middle, which is called a median. The whiskers represent high and low references for excluding outliers. So if we have outliers, they're usually on the left side of the mean here or on the right side of mass here on this particular figure. You can also define where the box starts and where it ends, how the whiskers range and so on with different presets. But I think in the beginning would be good to use the settings that you get by default, so to say. And when do you use box plots? So the advantage is that it can organize large amounts of data. So it's very good for that kind of situation. And it visualizes very well outlier values. So this is also a very good point. But there are also some disadvantages. So it's not really relevant for detailed analysis because at the end of the day, it provides a summary of the data distribution and not a lot more than that. So they're usually used when you want to compare between multiple groups to provide high-level information, to see where the main bulk of the data is and to make comparison between different groups. If you think about having different groups of box plots plotted next to each other, and we will see in the future a graph just like that. But how do we interpret the box and the whisker? So let's look at that. So the construction of the box is based around the dataset's quartiles, and these two, the lower quartile and the upper quartile. So the first quartile is essentially this value Q1, which is greater than 25% of the data, then less than the other 75%. Now, the second quartile, which sits in the middle, divides the data in half. We also know it as a median. I've mentioned it many times. And the third quartile, or the upper quartile, is larger than 75% of the data and smaller than the remaining 25. And then in a box and whiskers plot, the ends of the box and in certain line mark the locations of these three quartiles. So exactly what I said. Now, an important thing to remember is the distance between Q3 and Q1. So this distance, it's called an interquartile range, IQR. And this plays a major part in how long the whiskers are extending from the box, because each whisker extends to the furthest data point in each wing that is within 1.5 times this IQR. So any other data point further than the distance is considered an outlier, and it will be marked as a dot. So you would see dots here, like I said before, on the left side and the right side, which are outliers. Now, when a data distribution is symmetric, you can expect this median to be in the exact center of the box, much as you see it here. The distance between Q1 and Q2 then should be the same, just as you see here, then from the Q2, so the median to the Q3. And outliers should be evenly present on either side of the box. We don't really have outliers represented here, but if we did, they would be like that. Now, if a distribution is skewed, we have a different type of situation. Then the median will be not in the middle of the box, obviously, and instead of it will be off to the either of the sides, depending how it's skewed. You may also find some kind of imbalance in the whisker lengths. So where one side is short with no outliers, and then the other one has a long tail with many more outliers. So then it will be represented in the outliers, either on the left side here or on the right side of the box plot. But now let's look at something else. So one alternative to the box plot is the violin plot, and in the violin plot, the distribution of each group. So if you have three groups like we have here, A, B, A, C, that are plotted next to each other, here you see outliers that I explained about earlier on. Each of these groups is indicated by a density curve in a violin plot, as you can see here. And in this curve, each data point does not fall into a single bin like in a normal histogram, but contributes to this volume of data in the total distribution. And these are nice because they are compact, and it's a compact way of comparing the distribution between groups. Now we can have all kind of additional markings that we could add to these violins plots, like you see here, but somehow the plot becomes a little bit noisier to read, and maybe they're not so advisable. Especially, you only have three groups here, but imagine if you had like 20 groups, then you have all these lines, and it might become a little bit cumbersome to interpret. But now I would like to look a little bit at a special case, at some cancer analysis. So what you see in this figure is essentially hierarchical clustering using patterns found in gene expressions as group samples. So in this to the right, you can see clusters. This is the cluster dendrogram. But what you can see there is that it's very congested. It's impossible, not difficult, but it's impossible to really tell what is going on there. There is a limit in clarity. You cannot identify the subtypes of cancer, which is the whole plot of the class, the whole point of the clustering. So what we try to do here is really to recognize the nature of cancer and the nature of its subtypes and so on. On the left, here we have the number of clusters. And this kind of graph, based on criteria, different criteria, this kind of graph was obtained by a Euclidean distance that measured the similarity between different gene expressions in different patients. So clustering without prior knowledge of the right number of clusters can lead to misleading interpretations. So to avoid this, we employ different methods to determine a range of clusters based on different criteria. So here we have this bar plot, which you can see plotted on the left over here, where we show how many criteria supported each potential cluster count. So from the graph, you can tell that 3 clusters appear as the optimal choice. And what we can do now is get to the PCA analysis. So to reduce the number of clusters here in this dataset, like I was saying before, 3 is a good number of clusters because this is something that we can easily visualize and interpret as humans. So what you can see here is a PCA scatter plot of breast cancer gene expression data, which shows the molecular differences across 3 cancer subtypes. So you can see them in blue, yellow, and then gray. Specifically, the blue and yellow subtype shows different gene expressions variation, and this, you can see them on the left side and the right side, and this suggests possible differences in cancer prognosis, in treatment responses, and so on. Meanwhile, the gray type is overlapping with them and suggests that it shares both shared but also unique characteristics. So it shares some characteristics with the other two, but also it has its unique characteristics. And this means that these cancer patients in gray might need customized treatment approaches. So linking these subtypes with clinical results will give us more information for tailored treatments. And this example, this PCA example, is just one of the many examples that we can have. So let's do a little bit of a recap. As I'm closing this video, let's recap why EDA is important. So it's important for understanding data structure. We can familiarize with the data sets. We can see the number of features, their types, data distributions. And this knowledge is essential for choosing the right analysis or the right prediction methods, the right model later on to use in feature engineering and so on. We can identify patterns and different relationships by using visualizations, statistical summaries. We can, by employing EDA, we can uncover hidden patterns, different relationships between variables. Then we can, like I was saying earlier, we can improve feature engineering and model development later on. But we can also detect anomalies and outliers. We can spot errors or unusual data points that could impact negatively our results. Then in statistical testing, for instance, statistical models often rely on different assumptions about the data distribution or the independence or the dependence of variables. And with EDA, we can check these assumptions, we can draw conclusions, and so on. We can inform feature selection in engineering later on, like I was saying. And also we can use it for optimizing model design, to select more suitable modeling techniques. Then it facilitates data cleaning. So you can identify missing values, you can identify different errors in data, which are really important it's really important to have data quality and data integrity before you go further down the line in your pipeline with different types of analysis. And then another thing that is very important, and I mentioned many times that it's very important in data science is communication. So EDA enhances communication. By employing these visual and statistical summaries from EDA, we simplify the process and how we convey the findings, how we justify different conclusions, how we really get our point across to everyone else. So this was the exploratory data analysis. Thank you for listening and see you in the next video.